Alright guys, so for today's video, we're going to go over physical properties, Newman projections, and chair conformations. So start off to go over physical properties really quickly. Physical properties is just going to cover solubility, I'll cover that, boiling point, and melting point. Okay, so in regards to solubility, solubility is just how well two different types of molecules or solutions are gonna be able to like coalesce together and to form like a very homogeneous mixture. Okay, so something is soluble when those two things can interact very well. Okay, so what this is going to depend on is going to depend on the type of intermolecular forces that that a molecule has. So, for example, you want to remember the rule that like dissolves like. So we're going to look at whether something has polarity, can perform hydrogen bonding, things of that nature. So, for example, H2O and a carbon chain, they will not be very soluble together because H2O is a polar molecule and it performs hydrogen bonding, and a molecule like, for example, so H2O and CH3, CH2, CH3. If I mix these together, these will not be very soluble. Okay, we have a nonpolar molecule mixed with a polar molecule, and as such, the thing that's produced is not a homogeneous mixture. Okay, so we can look at some examples of that later, but it's not that difficult of a topic. What this really comes into play is just helping you make implications about what the boiling point of certain solutions will be. So if you say like and understanding like how strong the interactions between molecules are. So like if I have a beaker full of CH2, CH3, CH3, CH2, CH3, and I have a beaker full of water, which one will have the higher boiling point? It'll likely be the water, because the water molecules can interact with each other and form a stronger interaction, stronger bonds. But the this ethane right here, it won't be able to really interact with the other ones besides van der Waals interactions or the London dispersions. Okay, so it's a very weak interaction. Okay, so the stronger the interaction between the molecules, the higher the more energy is going to be required to reach boiling point. Okay, so that's just a small preface. So solubility, just remember like dissolves like, and try to see what kind of properties, characteristics that the molecules have, and then you can like make assumptions about their ranking of boiling point, stuff like that. For boiling point, when we're just dealing with like carbon chains, typically the trend is that as we increase the mass, so for carbon chains, we're just going to look at the trend goes along with the mass. So, and what this corresponds to is the amount of surface area. So as we increase the mass, we typically increase surface area, and the more surface area we have, the more energy it's going to require to reach boiling point. Okay, to have all these molecules moving around and freely moving and having a lot of energy. Okay, whereas when we're in either liquid or solid state, the molecules are very compact and they're close together, and they have very low energy. Okay, so as you increase the mass, you increase the boiling point. But what happens when you have branching, as we can see here, all these have the same number of carbons. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, so on and so forth. Okay. As we increase the amount of branching, so branching outwards, doing these groups, and eventually you have something like this, we're going to decrease the boiling point, and that happens because you can look at it two ways. You can look at it straight up from the perspective of looking at surface area, and if we look at surface area, as we increase the branching, we decrease the amount of surface area, right? But another way you can look at it is, imagine I have a beaker, right? And in this beaker, let's say I have a bunch of these things, okay? And they're all just kind of like this. I'm going to try to draw them as close together as possible. You get the idea. Okay, these are just a bunch of turret beetles. And then let's look at a beaker full of this guy, right? So, all right. So as you can see, this molecule over here is very bulky. It has a lot of arms stretching out, and it prevents itself from interacting very well with the other ones around it because it's just so much to occupy so much space. So it's very crowded. So as I decrease the energy in this environment, I decrease the temperature or whatever, it's going to be really hard for these things to compact together and form like a very, very like I guess very compact, group of these molecules. Whereas when I have over here, I have this, what is it, 3, 4, 5, 6, all these hexanes. They are just aligned. They just pile on top of each other, so they become very compact much more easily. So as I increase the energy in both of these environments, these are going to be able to begin moving around much more quickly, much more rapidly than compared to this one. So these molecules are going to be able to become more compact, and it takes more energy to take them out of that state, whereas these, they are not that compact, and take less energy to take them out of that state. So that's just two ways you can look at it. A melting point is same thing, just greater the molecular weight, the greater the melting point. So it's a common trend, but it's just not as easy to just kind of look at a molecule and say, oh yes, the melting point is increasing in this like linear fashion or whatever. So it's more random. But usually she'll ask about melting point. Okay, I mean usually she'll ask about boiling point. All right, so moving on from physical properties, not that hard. I want to look at Newman projections now. So a Newman projection is a way to draw to represent molecules in three-dimensional space. Okay, so I'm just going to be looking through her notes, and I'm just going to show some examples. All right, and it's not that difficult. It's just a way to look at a molecule from an angle and see certain certain, I guess, states as it's rotating. So like I said before in a previous video, I'm just going to draw something very basic. So like I said, pi bonds cannot rotate freely, right? The things that are coming off pi bonds, these are not rotating, right? The whole molecule itself is rotating in three-dimensional space, but for sigma bonds, like we have here, single bonds, these are all rotating freely. Like I said, it's like a steering wheel. These are all rotating, right? It's like a steering wheel, okay? And so these are all rotating in three-dimensional space constantly. But there are states where the way these things rotate, they rotate in a fashion that allows the molecule to achieve a lower energy state. So it's not going to stop it from rotating, but it's just there's certain states as it's rotating that they're lower energy. Okay, and it's very important for us, to look and understand when that happens and why that happens. So the reason why this happens is because around every hydrogen is very small, but I'm gonna show you a different one. Okay, so let's say I have this this carbon and it's next to a CH3, right? And over here it has another CH3, right? And let's say it just has a hydrogen, and then this is bonded to another carbon, and let's say it just has a hydrogen. Say it has a CH3 group. Sorry, it's missing. All right, and so let's say these are my fixated carbons. Okay, I'm not turning these ones. Everything else around these carbons is turning. So just kind of like this previous example where I was turning things on the outside. So let's say this is one big group, this is one group, and this is one other group. So 3 groups on this carbon and 3 groups on this carbon. And all these are rotating in space. Okay, all these are rotating, right? So as these are rotating, there are points where this group is interacting with this group or this group or this group, right? There's points where these are interacting with each other, where they're close. So let's draw an example of that, what I mean by that. So there's a point where they are near each other, okay? Where they're near each other. So what do you guys think is happening as these groups are close to each other like this? Well, what's happening is these groups are bulky, right? They're bulky in three-dimensional space. They're kind of like balloon, each carbon with its hydrogens or lone pairs, even for like, for example, oxygen. Um, they're kind of like giant balloons. So think of it as kind of like this, right? And these interactions, so like imagine these balloons are over here, and they're kind of just they're all up in each other's business. Like they're interacting. So right here you have a lot of um, interaction, and we wanna that interaction is not favorable, right? Because these molecules are going to repel each other, and their electron environment. So those electron environments are going to interact negatively. So it's not a favorable interaction. And so what molecules want, they want their groups to be as separated from others as much as possible, right? So these electron environments want to be as far away as possible. Okay, so we want them to be as spaced out and free, and that's what's going to be the lowest energy. But when I push them together, that's those it's electrostatic interactions. But there's a word for it. But in general, it's just we don't want those to be near each other. And so this is essentially what this diagram is representing. So we have a butane, right? And I'm just gonna clean this page up. Okay, put this back. And what we have here, we have a butane, okay? And I want to show you guys what this looks like in three-dimensional space. All right, so I'm just gonna draw a nice little butane. So one, two, one, two. All right, so I have that, and I want to put this in 3D. All right, so I have this over here. So 1, 2, 3, 4 is my butane, and essentially, what we're doing with this, we're looking at it kind of like this. All right, I'm looking at it from this angle. All right, I'm looking at it kind of like that. I don't know. You're kind of looking at it like this. So, and what they'll tell us to do is, and these are the hydrogens, right? This is carbon. This is a carbon. This is a carbon. This is a carbon, right? Wait, this is yeah. Okay, this is carbons, and these are the hydrogens coming off of them. And what we're doing, and you can see how they kind of have the bulbs, right? And so what we're doing here, we're going to look at the molecule, and we're going to look at it in respect to in between two bonds. So this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. And what she tells you is she kind of splits it in half, right? She may split it in other anyways, but she'll say, I want you to look at the Newman projection of this molecule from the perspective of the 2-3 bond angle, okay? So she'll tell you in between the 2-3 bond angle. So what that means is this carbon right here was that carbon that we were looking at, right? So like remember my drawing? And I had groups coming off of it. It's always 3 groups. So she's saying this is carbon 2, this is carbon 3 in respect to butane, right? And butane has, this one has a CH, right? It has a CH on it. It has 2 CHs, right? This is a CH2, and then it has a CH3. And this has a CH3 on it at the end, and 2 more H's, right? So this is what we're drawing, just to make it very clear. And so we're looking at this molecule at this bond right here, right? We're looking at it right here, and I'm looking right here. She always draws the eye, right? Imagine this is an eye, okay? Whatever, right? So I'm looking in this direction, and I'm looking at the molecule, I'm looking at this carbon and this carbon, I'm looking at the groups that are coming off of it, and I'm looking at how they interact. So right here, this would be these two hydrogens and this whole group over here. And you can see how big this CH3 group is. And what we're doing, I'm trying to decrease the interaction between all these groups in space, okay? And I want as little interaction as possible. And the way it looks as a Newman projection, when we set this up, so what we do is you draw a circle, okay? Right, you draw a circle. And on the circle, right, you have your three groups. So 1, 2, 3, okay? So the circle represents the carbon, this carbon right here, right? And then what we also draw is we draw what's supposed to be this is supposed to be the back of it. So this is actually this back carbon, I believe. And then we draw the front, right? You can draw whatever, and we draw the front. So imagine I'm looking at it like this, right? Essentially what I'm doing. I'm looking at it like this. So this is C2, this is C3 down here. So I'm looking at it like this, okay? And so this is the front one, okay? This is the front one. And this also has 3 groups, okay? So what you do at first, doesn't matter how you do it, we're just going to put the 3 groups on each one. So I'm doing the back one, and now I'm doing the front one. And I've drawn a Newman projection. This is a complete Newman projection of this molecule butane. And you can find this one right here, okay? I just drew the anti one. We'll talk about that, okay? So this is the Newman projection for butane along the 2-3 bond angle, all right? And so what happens essentially, these are constantly moving around. I have many Newman projections for various states as this molecule eventually reaches after this one, then we go back to the original. Right, this is actually the original. So 360 degrees of rotation have been performed, and each one of these is a degree of rotation. So 60 degrees, 120, 180, 240, 300 is just turning one of the groups. So the way you would do this is you keep one side the same, right? So either you keep the front or the back the same, and you turn turn the other one. So what I normally do, I keep the back one, the circle, and I turn the front. So I just move those around. And if you keep turning those, so turn this here, and then, this would come down, and this would come over here. And then do that again and bring this again halfway, and keep doing that. You would get every single one she's drawn over here. All right, so what these represent are just the different energies. She's corresponding the energy of each one of these states. And I have drawn the lowest energy one, right? The most energetically favorable one. And let's look at why this is the most energetically favorable. The reason why it's the most energetically favorable is you have your biggest groups, your CH3s, completely opposite to each other, 180 degrees away. So because I've made them 180 degrees away from each other, this is the lowest energy state. And you can see if we look over here, and I'll show you the highest energy state. The highest energy state is going to be this one. Okay, hopefully everyone can see it. And this one's kind of hard to draw. Let me right. I'm just going to draw the front one because it's easier to draw. And then I'll draw the things coming off of the circle. Okay. When everything is on top of each other, so I have the hydrogens on top of each other, even though they're the smallest. And then I have both the CH3 groups. Okay, so I'm just going to draw it in line angle like that. Actually, no. Just the CH3. So imagine, I'm not going to write it all out, but the CH3 groups are on top of each other. And when they're on top of each other, I have the highest energy states, right? These are called eclipsed, okay? Eclipsed, right? And when they're in the lowest energy state, this is called anti, right? You may have more than one anti, depends on how the molecule looks, but it's when your biggest groups are anti to each other, okay? And then you have other states that are in between, right? Actually have two types of eclipse. There's various types of eclipse because obviously you can have eclipse where the hydrogens are eclipsing, and you have a CH3 eclipse with another H and another CH3 eclipse with H. But there's totally eclipse where your biggest groups are on top of each other. So this is the totally eclipsed, and then there's other minor eclipse. But the totally eclipsed where your biggest ones are on top of each other, that's the highest energy. And then where your biggest groups are opposite from each other, that's your lowest energy. And then your states where you have things in between, like this, right? You have a CH3 like this that's 60 degrees away, like this in the middle. It's not the anti-state, but you have them kind of close to each other, but not on top of each other and not opposite of each other. This is gauche. And gauche can also look anything like this. So these are the various states. And usually she'll ask you to draw either the highest energy state or the lowest energy state. And that's what you really need to know how to do. Okay? So it's not that hard. And from here, we're just going to do some examples. All right? So I'm going to take an example from the workbook. Okay? In the workbook, it says, I'm going to put this problem. Circle the structures that represent a conformation of 2,2-dimethylbutane along any CC bond. Okay. Actually, I don't like this one. I like it, like number 15 more. Alright, let's do this one. Okay, consider the molecule 3-chloro-2,5-dimethylhexane. Looking down the C3C4 bond, draw the Newman projections of all three staggered conformations of this molecules. So staggered is, I believe, just another word for saying, let's see, because she didn't have that. All right, just look it up really quickly. I believe staggered is when it's similar to the Gaussian anti-formation, okay? So staggered is another word for drawing it out like this, okay? Staggered this is staggered, okay? Okay, so that's staggered. All right, so it says consider the molecules. So let's first draw the molecule. This is where naming comes in handy. So I have 3-chloro-2,5-dimethylhexane. So I have a hexane. Let me just draw a hexane. So 1, 2, 3, 4, 5, 6. On the third carbon, I have a chlorine. And then I have on the second carbon, I have a methyl group. Okay, so 1, 2, 3, 4, 5, and then I have another methyl group right here. Okay, and this is the C3C4 bond. So this is carbon 3. This is carbon 4. Right, so 1, 2, 3, 4. Okay, and so I'm separating these three parts. So I'm looking at the three groups that are coming off of this carbon right here, and the three groups that are coming off this carbon right here. All right, so the way I draw that, I'm going to draw my crappy circle. I'm going to draw my back circle, okay? And I'm going to start putting the three groups. And I'm going to draw the front circle and put those three groups. So on the front circle, off of this carbon, what do I have? I have another bond here. There's a hydrogen, invisible hydrogen over here. Okay? There's two hydrogens. All right? So, yes, so there's two hydrogens on those. All right, so on this carbon, the front, I have the hydrogen, I have a chlorine, and I have an isopropyl group. So that's what it looks like. I'll call it IP, isopropyl. That's how it looks like on the key. But you could have drawn it out, doesn't matter. And then on this carbon over here, I have two hydrogens, right? And then I have another isopropyl group. So what state have I just drew this randomly. I wasn't thinking. So what state is this, right? I have two of these, they're at angles, so this is a gauche. All right, this is gauche. But what is she asking for? She's drawing circle the least stable like this least stable state, and just draw all three staggered conformations. So I drew one staggered. Okay, And there's other ones, right? So she doesn't want us to draw them where they're eclipsed. She wants me to draw all the staggered ones. So let's draw another one, right? And these are all just gonna, this is the how a staggered looks, right? So I drew these next to each other. So now I'm gonna draw, so on the front one, I had an isopropyl group, I had a chlorine group, and I have a hydrogen group. All right, and the first one I drew the isopropyls next to each other. Now I'm gonna draw them kind of away, all right? Isopropyl, all right? And now I'm just gonna put the other hydrogens. Okay, so that's the next one. And let's do another. All right, so now I put them away, and now I need to do one where the isopropyls are again probably next to each other. So in the beginning, I had it like this. So I had isopropyl. Okay. So I had isopropyl. I put a chlorine. I put the hydrogen. All right. So I already had one where I have the chlorine next to the hydrogen and the isopropyl, and I had isopropyl, hydrogen, chlorine, and now I'm gonna have another isopropyl. This is actually a very uncommon way of doing this question, but she doesn't usually ask for something like this. But what she asks for is just to draw the least stable, the least stable or the most stable. So it's kind of redundant, I think. All right, so I think this is the other one. Okay, these are very similar. That's why I was having a hard time just making sure I was doing right. But these are your three. And if I was to write circle which one is the least stable conformation one, right? It's going to be the one where I have let's see. Right, I think I actually do this last one wrong a little bit. So I have this one over here, and yeah, so I shouldn't have that over there. I should have the isopropyl over here. Yes, that's what I'm supposed to draw. Okay, my bad. All right, so this one is going to be my least stable. All right, this one's least stable because I have three bad interactions. I have a really big chlorine group, right? Chlorine has all these lone pairs, and then I have it interacting with the isopropyl group, and the isopropyl group is also interacting with this isopropyl. So I have three big interactions. Okay, this one, my biggest groups are away from each other, and then my chlorine is, only next to one of them. And then in this one, my groups are next to each other, and my chlorine is away. So this is my least stable one because it's the highest energy. All my biggest groups are next to each other. All right, so that would be how you do this one. Let's do another one. All right. Let's do one from an exam. How about that? All right, let's see how she does it. All right, so this is how it looks on an exam. So viewing the molecule along the C3C4 bond, construct a Newman projection of the most stable conformation of 2,3,4 trimethylpentane. All right, so I actually want to do this over again because I don't want you guys to see what it looks like in case we had to draw it. All right, so 2,3,4 trimethylheptane. Heptane is how many carbons long? It's 7 carbons. So I draw 1, 2, 3, 4, 5, 6, 7. All right, and then I have 2, 3, 4 trimethyl. So methyl group, methyl group, methyl group. And then I'm looking at the C3C4 bond. So 1, 2, 3. This is C3, and this is C4. Okay. And I'm splitting it right here, and I'm looking at everything that's coming off of these. So let's draw my most stable. So that's what she only asks for one usually, right? So most stable is always going to be staggered, right? Where you have like this, right? Everything not eclipsed. So anti is just a form of stagger that's very stable. So what I do, first I need to look at what groups I have off this carbon. So I have invisible hydrogen, I have a methyl group, and then I have an isopropyl group. And then over here I have a hydrogen that's invisible. I have a methyl group, right? And then I have this 1, 2, 3, right? I have an ethyl, okay? Three carbons. So I'm going to, this is the front, so I'm going to draw the most stable. So that means my biggest groups are away from each other. So this is my isopropyl group, right? 1, 2, 3 carbons. And then what else does it have on it? This has a methyl group. So this is fine like this, and I'm gonna leave it like that, and then a hydrogen. Okay? Over here, what do I have? I have a methyl group and I have an ethyl group. So my biggest group on this side is the ethyl group, and my biggest group on this side is the isopropyl group. So what I want opposite of each other are going to be the isopropyl and the ethyl group. So this is 1, 2, 3. Okay, so these are opposite now. And now is all that's left is the CH3. So it doesn't matter where you put it, right? It does matter. Okay, so on the front I put this, I'm missing a CH3, so this goes here. Right, and obviously on the back I don't want to put the CH3 because there's some interaction there. So I want to put my other CH3 that's present over here, and I'll put my last hydrogen over here. So try to make everything as opposite as possible. So this would be the lowest energy state. Okay, and to check if I'm right on the answer key, this is what she has. Okay, this is the answer. Right, this looks like what I drew, right? Looks the same, just flipped. All right, so it's not too bad. Just be able to identify, be able to draw your molecule first of all, and then identify the 3 groups that are coming off. So 1, 2, 3, 1, 2, 3. Okay, not too bad. If we need to do more of these, we'll do more. But I think we're done with Newman projections for now. All right, the next thing that I want to do, and I'm just going to start this off by looking at her notes again. And what we're going to do now, we're going to look at chair conformations. Okay, and I'm going to talk about what the heck a chair conformation is. And this is from Bean's notes, so all this belongs to her. So, just using this for teaching purposes. So, I don't know if she's talked about it already, but what is a chair? Okay, a chair is just a way of saying how a cyclohexane looks like in 3-dimensional space. So cyclohexane is just the cyclic just means ring, form of a 6-member chain, right? This is what cyclohexane looks like. Okay, should I do that? Looks like this is what cyclohexane looks like. So what cyclohexane is doing, this is, I'm gonna draw all the hydrogens. And like I mentioned before, molecules are always trying to reach a lower energy state. They're doing everything they can possible to be as low energy as they can. So one way for cyclohexane to be low energy is by going into these chair conformations. So it has a lot of these hydrogens, it has all these interactions, and what it's trying to do is limit the interactions of all these molecules that are surrounding the outside of the ring. So it wants to limit these interactions as much as possible. And like I said, with Newman projections, all these are like little bulbs, okay? They're all bulbs. So it just, all these electron clouds, that's the word I was looking for earlier, electron clouds, right? And so I'm going to show you using this modeling device. Okay, so this is a cyclohexane, and let's see it in 3D. Okay, so this is what cyclohexane looks like, right? So we have all these molecules that look like this, and so all these things are interacting on the outside of the ring. All these things are interacting, all these bulbs, and these are just hydrogens, right? I could have even more things coming off if I wanted. Look, if I'm making it even more crazy, stuff like this. So it becomes even more interaction. Look at this. This is just single methyl groups. Look how much crazier it looks. So it's a lot of interactions that are happening. And what these cyclohexanes are trying to do is that they're trying to go into conformations that allow it to have lower energy and limit the amount of these interactions. So same thing with Newman projections, where we try to move the big groups and move the groups away from each other so they can limit their interactions and have lower energy. And that's exactly what's happening here, except it's happening on a ring. Okay? So just like with the Newman projection, the molecule goes through various forms, and then it ultimately will reach its every cyclohexane has two chair conformations. Okay? Has these stable formations and has a very unstable boat formation, right? And then it reaches these chair ones. Okay, so they look like chairs. And essentially, all we're doing is, and the way you're going to be tested is, she's going to give you a cyclohexane, right? She's going to give you one or two, whatever. Actually, let me just show you. Okay, we're going to learn through test examples. Alright, I still have more concepts to teach, but we're just gonna look at it. So she'll give you this. She'll say, draw the more stable chair conformation for each of the substituted cyclohexanes shown below. So it's two separate cyclohexanes, and for each of them, you have to show which of the chair conformations is more stable. So I said for each cyclohexane, there is always two chair conformations. One of those chair conformations can be even lower energy than the other, so they're not the same, unless the molecule is just hydrogens. That's why in the graph that I showed you, that's why the energy level was the same at the bottom, because it's just hydrogens. There's nothing unique about that cyclohexane besides the fact that it has hydrogens on it. So these are more unique, right? The environments are different. So one chair conformation is not going to be the same as the other, and it's not going to have the same energy. So she wants you to show which one has the lowest energy. And the way that we do this, and the way I do it, there's a harder way, and I think I've found like an easier way, is we have to first we have to convert these cyclohexanes, right, into chair conformations. So we have to draw it, right? This is a chair conformation. Okay, if you're good at drawing, this is a chair conformation, okay? All right, so the long way is drawing both chair conformations. So the opposite chair conformation is just flipped like this. So you just draw these points out, okay? And if you notice, there's six corners. So 1, 2, 3, 4, 5, 6, okay? And 1, 2, 3, 4, 5, 6. All right, and these are the same molecule, just flipped, and they have different arrangements of things. Okay. So so the way that we're gonna do this, so I'm gonna show you first the long way, and then we can look at the easier way. So let's say I was trying to draw A, okay, and I was gonna try to convert this into a chair conformation. I'm gonna start with this one first. So the first and foremost thing that you do, it's arbitrary. You choose an arbitrary direction and number along the ring. So 3, 4, 5, 5, and 6. All right? So you choose an arbitrary direction and you have to stick to it. And then you go to your chair conformation and you just label. So 1, 2, 3, 4, 5, 6. All right? And then when you go to the flipped one, all you do is you bring this down. And I went clockwise, so I'm going to keep going clockwise. So 1, 2, 3, 4, 5, 6. So all these are relative to the original one that I numbered, okay? And now I have to put things on it, all right? And this is where some decision making is. So I'm going to explain these dashes and wedges really quick. Dashes and wedges are, so like I showed you with this over here, in 3D space, I'm going to delete this one, I'm just going to put the regular cyclohexane, okay? In 3D space, dashes and wedges are used to represent in and out of the page. So it's up to you how you want to refer to them. right? It's not important to know which one's in, which one's out, but when you decide that a certain color is in, you keep it as in, and the other one is out. So for example, if I said I want dark wedge to represent out and dash wedge to represent in, then you're gonna be consistent, okay? Not just flip everything around. So what these represent, these are the wedges essentially, okay? So one is going, into the page, and this one is going out the page. It's coming at me, right? These are coming at me. All these on the side are coming at me, and these are all going in on this side. So what we're doing is I'm going to decide which one I'm going to make what's called equatorial or axial, right? And so to go back and show you guys based on her lecture stuff, because I forgot to show this, just to bring this over here. All right, so this is her notes. And so I'm gonna just show you this. I'm gonna look at this one right here. All right, look at this this representation right here. Okay, when you have lines coming out of the angles, straight lines coming out of the angles like this. Okay, this is not the light one, but you can see it's very dark shade over here. When they're coming straight out, so it's always when the lines are coming out of the angle. So when the lines go in the direction that the angle is pointing, this position is called the axial position. Okay, this is called axial position. There's a second line, right? Because each carbon on the ring has two groups. The second line is called equatorial. Okay, equatorial position. So the line that's not going in the direction of the angle of the bond, right, is called equatorial. Now, equatorial is always more stable than axial because it has the least interaction in three-dimensional space. It's going outside, it's going away from the other groups of the ring. So equatorial is where I want all my groups to be. If I want to maximize as many groups as possible on the equatorial position, as much as possible. So, given that, right, knowing that I have the axial position, I have equatorial position, this axial, this equatorial, this is equatorial, this is axial, right? So what I have to do now, first I'm going to redraw my thing because it's ugly now. It was always ugly, but I'm going to redraw it. And now what I do is I'm going to look at one of the groups, right? And I'm going to look at any of them, right? I'm going to look at number one, and I'm going to say this dash, I'm going to say it's in the axial position, okay? I could have said it's in the equatorial. It's my choice. But the reason why I can say the reason why you have a choice is because in one chair conformation, this is going to be axial, and then the other one that you're going to draw, it's going to flip and it's going to become equatorial, okay? So that's the beauty of it. In one chair conformation, it's going to be one way, and then the other one, it's going to be the other way. So right now, I chose this dash wedge, right, to be axial, right? And this is number one. So this is number one, this is number 6 over here. So I'm going in this direction. I chose this to be axial, so I drew a CH3 group like that. All right, so that's 1. Now you do, this is 2, this is 3, 4. All right, so now that I've said dash is axial, it doesn't mean dash is always axial. So what's happening along this ring and along the chair conformation, right? There's always a light and a dark wedge. There's always, on every single one of these, is a light and a dark wedge. Okay, they're just not shown, and even these have them. So light wedge here, I said it's axial. I chose that to be axial, but light wedge over here is now equatorial. It changes. It flipped. So every time you go one carbon down, what was before is flipped. So light wedge here is axial. Light wedge here is now equatorial. Light wedge here is now axial again, and now light wedge over here is equatorial. All right, so on carbon 4, this is the axial position, this is the equatorial position. Actually, I think it goes this way. This is the equatorial position. So on the equatorial position, I have a tert-butyl group. This CH33 looks like this, right? It's coming up from the molecule like this. That's what it looks like. That's tert-butyl. If you ever see the CH33 coming off of a carbon, that's equatorial. I mean, it's T-butyl. So it looks like that. Now, dash is equatorial here, and then over here I have a dark wedge. So now, over here, let's go back to my beginning one, my reference, right? The first one you choose is always your reference. So in the beginning I said dash here is as axial. Now dash over here becomes equatorial, but that means dark wedge now is axial. Okay? So it flips. So in the beginning dash is axial, then dark wedge becomes axial, then dash is axial, then dark wedge is axial, and so on and so forth. So over here, so basically essentially one carbon away from each other, the opposite colored, so the dash and the wedge, they're going to be the same, right? So over here, dash is equatorial, and then over here, the wedge is also going to be equatorial, because now the dash over here becomes axial because it flips. So that one is axial, the other one is equatorial. I hope everyone is not confused. Okay, so you choose a reference, and then you start flipping and going across the whole molecule, and this will let you label whether the groups are axial or equatorial. And again, axial is just a way to talk about the position on the chair conformation. Okay. All right. So now let's draw the rest. All right. So I drew this one, and then over here in carbon 5, I have the CH3, CH2 on axial. So that looks like this. So 1, 2. Okay. So that's the first one. I drew one chair conformation. Now this chair conformation is going to flip and it's going to go to the other form, right? The other form looks like this. I'm really bad at drawing this with the mouse, but so now how do I label this? So now this one becomes 1, and then I maintain my clockwise way of numbering it. So this is 2, this is 3, this is 4, this is 5, this is 6. And now all that happened is now I'm going to look at my group. So I had a methyl group. Before here it was axial, right? It was A. That's not an A, right? Before here it was A, axial. Now it's going to be equatorial. Okay, so that's my methyl group. All right, so now 2, 3, 4. So I'm 4. Right? On 4, I had a T-butyl group on equatorial, and now it's going to be axial. All right? And then on 5, I had a ethyl group, right, on equatorial, and now it's going to be axial. So it looks like this. All right? Just try to see me drawing that. You know, I'll change the color. Right? So that's the ethyl group. Okay? So now I need to compare, right? And like I said, we want as many groups as possible on equatorial. But above that rule is that I want my biggest group on equatorial. So what that means is I need to figure out what's my biggest group on this molecule here. My biggest group on this molecule is the T-butyl group, right? So these are all my groups. I have this, I have this, I have this, and I have this. This is my biggest one. This is usually always the biggest. And what I want this to be equatorial. This is going to give me the lowest energy molecule. And it doesn't even matter if the rest two are axial. And it doesn't matter if this one is axial and this one are equatorial. It doesn't matter. As long as this one is axial, the molecule is not as stable as it could be. So what I want is this to be equatorial, and it doesn't matter if both of these are axial or whatever. So I'm going to look at my two versions of the molecule, and I'm going to look. All right, so I have this as equatorial. That's what I want. This is equatorial. That's even better. This is axial. Okay. Right away, I have the T-butyl group as axial. I know this is not as good as the other. So this is going to be the most stable energy form of this chair conformation for this molecule. All right? I hope everyone can see that and understand this. I know I'm kind of going very like kind of fast, but I think this is the best way to do it. All right. So I'm gonna show you the fast way of doing this problem. Okay. So the fast way of doing this problem is this. All right. It's you because a lot of people what they'll do they'll take up their valuable time on the exam drawing both chair conformations, which is completely unnecessary. All right. Unless she says draw both, that's the only time you need to draw both. But if she just says draw the most stable, we can immediately draw the most stable, and I'll show you how. So, like I said, we want our biggest group to be on equatorial. So what I'm going to do, I'm just going to draw my chair, and I'm going to look for my biggest group, okay? And I'm just going to do whatever. I'm 1, 2, 3, 4, 5, 6, okay? I'm still going in that order. So it doesn't matter. 1, 2, 3, 4, 5, 6, all right? And as my 1, all right? And what I'm going to do is, remember how I said before that I have the choice to choose what I'm going to make this molecule? So before, in the beginning, I made this axial, right? And now I can, instead of wasting our time, let's just go and look at the biggest group on here, since it's the most important. And I'm going to say, I choose you to be equatorial, okay? I choose you to be equatorial, right? Because at some point it exists, so I have the choice to make it to choose this state. I'm choosing equatorial, and I'm just going to see what it looks like. So I'm saying dash over here is equatorial. So this is my reference point. So dash is the hydrogen. My T-butyl is now equatorial. Now that dash is equatorial over here, that means over here dash is axial, and wedge is equatorial, right? And I hope you guys can see that now I'm getting the same thing that I got before, except it's taking me like no time at all. And then now, okay, so dash is axial. I always draw it as a light wedge. I don't draw the lines. That's fine too. Um, so dash over here is equatorial, and then dash over here is axial. Okay, so every time it flips one carbon to the next. So I just go to carbon 4, and I draw the axial one, and voila, I have drawn the most stable chair conformation much faster and without having to compare and doing all this other crap. And I think almost all the time this has worked for me always and saved me so much time. The only time where you have to kind of be careful is when you have another big group on the molecule. So let's say you had 2 T-butyls. You have to be careful and make sure that you're aware of what the other one could look like. Okay, so as long as when you draw the first one, all you have to know is that the other one is going to have all these things on the opposite position. So when this does the flip, this is going to be axial, this is going to be axial, this is going to be equatorial. So just be aware of what the other one looks like, just in case maybe it's more stable. All right. Now let's do B. So we're going to do it the quick way. So right away, I found this is the T-butyl group. I want this to be equatorial. So I'm drawing my chair. All right, and I'm just call this 1. This is gonna be 6 right here. Okay, this is 2, 3, 4, 5. Okay, so I always draw my 1 over here. My 6 is right here. All right, so my 1, I've drawn this as equatorial, and then on 2, so dash was equatorial. Now dash is axial over here. All right. So now I have 2, so this is now axial. And usually it's very safe to draw your hydrogens out because it makes it very clear to the TA that you're drawing this in equatorial, okay? So I'm drawing this H in equatorial very obviously, and so this is axial. All right, and then on carbon 4, so this is 1, 2, 3, 4 is down here. So dash is axial, now dash is equatorial, right? And now dash is axial, and now this is equatorial. So this CH3 is in the equatorial position on carbon 4. So that looks like this. And now I'm draw the hydrogen. All right, so I have drawn the most stable conformation. All right, and that's it. All right, that's literally all there is to it. Okay. Let's see. Is there anything else that's really important to do? Okay, so we did everything, confirmations. All right, so that's the end of this video. Next video will be about chapter 4 material, and we'll be getting ahead. All right.